Hey everybody, Mr. Troy here. This video's got some math, and some math, and some math, and some math, and it's time for maths with Mr. Troy. Alright, so we'll start this video a little bit differently. What I want you to do here is I want you to actually pause the video and try to do just this top division problem. It's tricky, it's not impossible, it's just meant to be a little difficult. So go ahead, pause the video, see where you get. Okay, if you're ready, I'm going to unpause in just a second, then all the work is going to appear. So make sure you've got your answer. All right, first step, we need a 1/2 x squared. Remember, you're thinking about what do I multiply 2x by to get 1x cubed. Next, a 3/2 x, because we have to multiply 2 by 1/2 to make this 3, or by 3/2. Now we catch a bit of a break. We are left with 8x here, and we can multiply by 4 to get from 2x to 8x. We are left with a remainder. So our remainder is 4. The way we are most often going to answer these questions, the way that you'd be expected to do them on the homework and expected to do them on a test, is to write plus the remainder over the divisor. Then, of course, for this particular problem, we would want to reduce our answer. So our final answer for this problem would be 1/2 x squared plus 3/2 x plus 4 plus 2 over x minus 2. Now I want to write this out according to the division algorithm. It looks like this. And here's what this means. Our original dividend is the quotient times the divisor with some remainder left over. So what this tells me is that the original dividend, or this original function, is not evenly divisible by 2x minus 4. It is 4 more than something that is evenly divisible. Now, what would happen if I plug 2 into this function, which is the dividend? So we can do that. We get 8 plus 4 minus 12, which is 4. Well, I wonder why that is. We're saying the two sides of this equation are equal. So if I plug in 2 to this, that's the same thing as plugging in 2 to the right side. Can you see what happens? Take a second and look at the right side. When you plug in 2, this set of parentheses is going to become 0, which means that all of this product is going to turn into 0, which means you're just going to be left with 4. More on that on the next slide. So that was an example of the remainder theorem. The remainder theorem says that if you do long division and get a remainder, that's the same thing as plugging in that value to the original dividend. Now, I used a bit of unclear words there, so I want to make sure that it's clear what I'm talking about. If I do division with this problem, my remainder would be the same thing as f of 3. So if this is my function, whatever my remainder is going to be the same thing as plugging in 3 to this function. Let me do the division really quickly. You can do this one or not. So I get this quotient of x squared plus 5x, and I get a remainder of 0. This means that plugging in 3, not x minus 3, but 3, to the dividend would give me 0. Now, because I have no remainder, I've divided out evenly, then this other theorem, the factor theorem, tells me that this is a factor of the original function or dividend, if that's how you want to think about it. Hey, I'm over here now. Okay, so we're going to go on in just a second. I just want to give you a chance to write those down and think about if you have any idea what's going on. Oop, that sounded bad. I mean, think about how happy you are about knowing that everything is going on. Okay, so here's an example of how we could use that. Knowing that this function has a 0 at x equals -4, show its complete factorization. So what the previous page tells us is that if plugging in -4 gives us 0, then x plus 4 should factor out. So to show that, for now, I'm going to do long division using x plus 4. I'll do this step by step so you can pause and follow along if you want to, or just do the entire problem yourself if you don't want to follow along step by step. So I get something that divides out nicely. It was, in fact, a 0, which means that x plus 4 was a factor. And I got no remainder. So remember, the things that you're supposed to know is that f of -4 is the remainder when I divide by x plus 4. And if that remainder is 0, then I should have a nicely divisible factor. Well, now where do we go from here? Well, our goal is to take this into from something new into something that we already know. I actually already know how to factor the quotient because I know how to factor by grouping. Let me clean this up a little bit and we'll put it on another slide. So we were able to use long division to pull out that one factor and give us this long cubic 4-term polynomial. And I can factor that by grouping. So remember, the way that you factor by grouping is you take out a common term, and you're going to know to factor by grouping when you see 4 terms. That's what's going to tell you that that's the time to do that. We're going to take the multiplier in front of each one of these same binomials, and we're going to make them into their own binomial. Then we're just going to see if we can factor any more, and in fact this factors because it's a difference of squares. So by just knowing a single 0, I was able to figure out how to factor that entire 4th power polynomial. Now, how would you know what might be a 0 of a polynomial? Well, the way that you would tell is by looking at the first term and the last term. So in that last problem, we were just given that something was a 0. But is there some way to know? So I want to start by looking at this middle one. If this were to factor, it would factor something like this. It'd have a 3x in front and an x in front. And the last terms would be something like -7 and +4. Or maybe not -7 and +4, but maybe something like +14 and -2. Right, so it would have something to do with this first term and something to do with this last term. And the same thing actually holds for longer expressions. So this is called the rational roots theorem, or the rational zero test. And what it tells you is that only certain numbers can be zeros for a polynomial. So for example, if I said, if I called this f of x, is f of 5 equal to 0? You could immediately say no, because you could say, well, there's no way that's going to factor with a 5 in it. Where would a 5 come from? It wouldn't come from the 3, and it wouldn't come from the 28, right? Because if this factors to, let's just say, I might be right, I might be wrong, but let's just say this factors to something like, I don't know, 3x plus 2 times x minus 14. That's not right, but theoretically, it's within the realm of possibility, right? So if it were to factor that way, our zeros would be x equals -2/3 and x equals 14, right? They're related to the things in the parentheses. So if I said, well, 5 is going to be a 0, that would mean that you could factor it like x minus 5 times something. And that's just not the case. It's just not possible. How are we going to multiply 5 by something in order to give me -28? So if you're asked to list all of the possible rational zeros, here's what you do. You list all of the possible factors, both plus or minus, of 28. So that's 28 and 1, 14 and 2, and 7 and 4, over all of the possible factors of 3. And that's 3 or 1. Now it's all of these different combinations. So the way that I like to think about it is I like to think about, okay, plus or minus 28/3 or 28, 14/3 or 14, 7/3 or 7, 4/3 or 4, 2/3 or 2, and 1/3 or 1. Now, it seems, like one of those little math things that I just came up with this great time-saving technique. My great time-saving technique is that instead of there being an infinite number of possible things that I could plug in and get 0, there are 24 things that I could possibly plug in and get 0. So I guess this saves you time if someone walks up to you and says, hey, buddy, can you plug in 5 to that function and get 0? You'd say, no way. No siree, Bob. Okay, so if you have things that are especially long, sometimes the way you want to organize it is by thinking of all of the factors of the constant term across, kind of like that, and then all of the factors of the lead coefficient down, like this. And then you kind of make this grid of all of the possibilities. So you could see where I'd get 28 thirds and 28 over 1, 14 thirds and 14 over 1, 7 thirds and 7 over 1, so on and so forth. Now, because you could put your plus sign here and your minus sign here, or vice versa, you need to consider that there are twice as many possibilities. So I know what you're thinking. Okay, so I have to come up with the 24 different possibilities, and then I have to do long division for each one. There's a faster way. So this is a method called synthetic division. Synthetic division is a way of doing division without writing out everything, or alternatively, a way of plugging things in because we can use it to find a remainder. So here is how it works. You start by writing out the coefficients. If you were to skip any coefficients, you would have to write out a 0 in that space. You don't have to write out any of the x squareds. You just have to remember that this is the 0 power, the first power, the second power, so on and so forth. So what you're going to do every time is you're going to drop the first term down, and whatever is here, you're going to multiply by this -4. The -4 comes from here. Then you're going to add those together and multiply again. And then add those together. And I find this quite relaxing. I don't know about you. And then add those again. And then multiply. And then add. It works so nicely. So here's what we found. We found f of -4, which is also the remainder when we plug in -4 or when we divide by x plus 4. Not only that, these numbers, they mean something. Let's go back to that previous slide. Look what we found here. X cubed minus 9x squared minus 4x plus 36. 1 minus 9 minus 4, 36. So this minus 4 represents x plus 4. And this represents the quotient. X cubed minus 9x squared minus 4x plus 36. This represents the remainder. So that's pretty great. It takes all of this work and it simplifies it way down to just this. So then if you have to plug in a whole bunch of different things, it's a lot easier. Okay, so here's a synthetic division problem. First, let's see. Can you set it up? Okay, so I'm sure you got this. Great job. Copy down the coefficients. Then drop, multiply, add, multiply, add, multiply,
according to Wikipedia,
add, and then multiply. So this statement right here is called the division algorithm. We have the dividend equals the divisor times the quotient plus the remainder. So now your job from here would be to see, can you find the other zeros of this function? You would start by trying to find all of the rational zeros that could work, and then you'd go from there. All right, so where we're going to pick up from here is we're going to see if we can find all of the other factors or zeros of this using that rational root theorem. All right, everybody. That was our longest video to date, and I know that you're going to take that information and you're going to squish it in your brain and you're going to process it and you're going to master it. Thanks for your hard work. It is greatly appreciated. Here's the theme song. All right, I have to go mow my lawn. You guys do your homework.